Welcome back to section 1.1. We went over this first part right here in class today, and now we are going to look at an example that walks us through the process of statistics. So statistics tells us information about a situation. So normally we have a question, and to answer the question we look at data. So let's look at this example. Let's say we are curious in knowing how many or what proportion of 13 to 17-year-olds have been prescribed medication. How could we go about doing this? Well, it's definitely not an option to survey all 13 to 17-year-olds and then ask if they have been prescribed medication. First of all, we don't have access to all of them. Second, that's a very personal question. We're not allowed to just gather medical information from teenagers. So we're only going to be able to look at a select amount of teenagers. We can't look at all of them. So what we could do is we could take a small group. Relatively small. And survey them. A small willing group, because not everyone wants to give up that information. Okay, so that's what someone did. The Gallup organization is a reputable organization that gathers information from groups of people. So for this study, the Gallup organization contacted 1,028 teenagers who are 13 to 17 years old and live in the U.S. and asked whether or not they have been prescribed medication for any mental disorders. Okay, so we are going to get some vocabulary words based on this example. First, this whole entire 13 to 17-year-olds in America, every single one would be what we call the population. The population is the entire group of individuals to be studied. So the population in this example is all the entire 13 to 17-year-olds. All right, and then notice in our definition, we had this word individuals. In this case, it makes sense because the population is humans, made up of humans. But our population could also be all butterflies in the world, for instance. And in that case, individual, we would still say that it's the entire group of individuals to be studied, because the vocabulary term individual is just a person or object that is a member of the population being studied. So in our case, what's the individual in this example up above? It's a single 13 to 17-year-old. So we can say that it is one 13 to 17-year-old. Just a single one. All right, and then what the Gallup organization did is they took 1,028 teenagers and gave them the survey. So that's an example of a sample, and that's our next definition. A sample is a subset or a smaller group of the population being studied. So what's the sample in our example? Our sample is the 1,028 teenagers, or I'll say 13 to 17-year-olds. All right, so let's say after we've gathered our sample and given our survey, we get some results back. And let's say our sample and study indicate that 50 teenagers out of 1,028 have been prescribed medication for a mental disorder. What is one way we can describe this result? Well, one way is we can look at the proportion of teenagers that have been prescribed medication. So that would look like 50 teenagers out of 1,028. All right, we can leave it as a fraction like that, proportion. Sometimes it's a little bit easier to break this down as a decimal, because then we can break it down as to a percent. So we can say something like 4.9% have been prescribed medication. I'm just going to abbreviate meds since I'm running out of space. Okay, so what we just did was a process called descriptive statistics. Descriptive statistics consists of organizing and summarizing data. So descriptive statistics describes the data through numerical summaries, like 4.9%, tables, and graphs. All right, and then when we're talking about a numerical summary from a sample, like this 4.9%, we call that a statistic. So a statistic is a numerical summary based on a sample. So we have a lot of definitions for statistics, right? So a statistic is a numerical summary based on a sample, and I'm just going to highlight sample. Okay, so riddle me this. What would it look like if we took the above descriptive statistic and applied it to the entire population? All right, so we're not really allowed to say then that 4.9% of all teenagers have been prescribed medication, because we know if we took a different sample of different teenagers and asked that same question, we're probably going to get a different proportion. So we have to keep that in mind when we start talking about the entire population. And that process, going from a statistic to the entire population, is called inferential statistics. And that's our next definition, and that's why statistics is so important. Taking information from a small group and applying it to the population. So inferential statistics uses methods that take results from a sample, extends them to the population, and measures the reliability of the result. So we have that 4.9% from up above. So when we extend them to the population, we know that if we take a sample, a different sample, we're going to get a different proportion. But if it's a good sample that represents the population, the numbers should be approximately the same. So what we do when we extend them to the population is we add some wiggle room. So let's say from 4.9, maybe we add and subtract half a percentage point. Okay, so that's us extending them to the population. We have to add wiggle room. And depending on how big our wiggle room is, if we have a large amount of wiggle room, we're going to be really confident. If we have a small amount, we'll be less confident. So let's say in this case, and we'll calculate all of this later in chapter 9, let's say that we're 80% confident. All right, so what I have written in blue does two things for the inferential statistics. First, we extended them to the population, and this 80% confidence measures the reliability of the result. Okay, so in general, we're going to see that we can take our statistic from our sample, and we're going to add and subtract. I called it wiggle room, but really it's a margin of error. So margin of error. And then the 80% confident part is referred to as the level of confidence. And both of those components are part of inferential statistics. And more on that in chapter 9. For For now, we just have to know that inferential statistics takes a result from a small sample and extends it to the population. Okay, so that example outlined the process of statistic. First, we had a question that we wanted to answer. So we call that the research objective. So our first step in the process of statistics is identify the research objective. All right. Then, once we have the question we want to answer, we collect the data through a sample. All right, and then once we have that data, we're going to describe the data. In this case, that was when we said that 4.9%. And then finally, step 4 is we perform our inferential statistics. And we say we will perform inference. And that is why statistics is so important, because we don't have access to entire populations most of the time. So we have to make conclusions about the population through small samples. All right, and this process of statistics walks us through our semester. Collecting data through sample, that's going to be chapter 1. We're going to get all our vocabulary words out of the way. That's chapter 1. Describing the data, we're going to be using charts, tables, numerical summaries. That's going to be chapters 2 through 4, where we're going to be describing data. And then the inferential statistics, before we actually hop to it, so I'll put it in parentheses, we have to bulk up our theory in chapters 5 through 8. And then the actual inferential statistics start in chapter 9 and go all the way to 13. All right, so the process of statistics outlines our course together. So let's go through this next example. I encourage you to pause this example since the previous one we just did together. Please pause it and see if you can do it on your own. Then come back and check your solutions. Okay, so we read through this question. The private financial group conducted a survey, and they want to know if employees were participating in an employer-sponsored automatic payroll deduction for a 401k plan to save for retirement. Okay, so first off, what is the research objective? It's essentially what I just said. If the U.S. employees between July 2010 and August 2010 were participating in this program. Okay. So what is the population in this case? Well, they wanted to know, they took a sample of employees in the U.S. between July 2010 and August 2010. So that's our population. So all employees, all U.S. employees between July 2010 to August 2010. Okay, what's the sample? The sample is that 1,772 U.S. employees. And as we continue in our paragraph, we'll find that descriptive statistics, 27% of the sample said they were participating. So 27% is the descriptive statistic. All right, and then finally, what can be inferred from the survey? So that's in this last part. The principal group reported that 27% of all employees participate in the automatic payroll deduction. And here's the inferential part, with a 4% margin of error and 95% confidence. Okay, so that's fine if you wrote it like that. I'm going to show you how the margin of error works exactly. So what can be inferred from the survey? That, let's see, here's 27%. I'll write it in a different color. Let's add and subtract that 4% margin of error. So 27 minus 4 is 23%. And 27 plus 4 is 31%. All right, so that, what can we infer? That 23 to 31% are participating. U.S. employees are participating. And we would have to say with what confidence? We would say with 95% confidence. All right, and there you go. Okay, so what we're doing in this example right here, when we're doing this 23 to 31%, again, we're trying to estimate all employees in the U.S. between these 2 months, okay? So we're saying that the actual population is between these two percentages. So we're really estimating something called a parameter. A parameter is a numerical summary, this time about a population. All right, so inferential statistics estimate a parameter. Inferential statistics estimate a parameter. Okay, so let's play a game, parameter or statistics. Parameter or statistic. So number one, suppose the percentage of all students on your campus who have a job is 84.9%. Is that a parameter or a statistic? That's right, it's a parameter because it's all students. So no mention of a sample. And most colleges, they have an entry survey where they ask that question. So they actually have access to the population. All right, so now look at this next one. Suppose a suppose a sample of 250 students is obtained, and from this sample, we find that 86.4% have a job. All right, so that means this 86.4%, since it's coming from a sample, it has to be a statistic. All right. And likewise, when we're talking about parameter, they're numerical summaries. So before that, 84.9% was a parameter. All right, so again, let's review just this process of statistic. We have a question about the population, okay? And we want to answer it. So how to answer our question, or how to answer the research objective, we make a random selection and have a small sample. And this is easy to work with. From our small sample, we get a statistic. And then we do our inferential statistics to estimate a parameter. All right, so we kind of have this cycle. All right, so the second step in the process of statistics is collecting data. So when we're collecting data, we have to know how to classify the data. All right, so let's look at these definitions. So data varies. So first of all, we call the data, it's called a variable because it varies. It can be thought of as characteristics, and there's different types of variable. A qualitative or categorical variable is a classification of individuals based on attributes or characteristics. So I like to look at that first word, qual, and I think quality. So it's a quality, and we describe qualities with words. So qualitative variables, think of things that you would use to describe with words. So maybe like eye color. eye color is brown, black, blue, green, hazel, stuff like that. Another qualitative could be the city you were born. Those are words that you describe that. Maybe majors, if you're in a school environment, what's your major or degree objective, et cetera, et cetera. So these are all the variables, and the values of the variables, we would say words. So for instance, I'm a math major, I'm an art major, I'm an English major, stuff like that. On the flip side, we have our quantitative variables, and it's a numerical measure of individuals. And not just that, those values can be added or subtracted and give meaningful results. All right, so that first part, quantitative, I think quantity. And quantity is a number. All right, so start thinking of some variables that you would, whose values would have numbers. So I'm thinking maybe weight, maybe number of cats, height, stuff like this. I do want to make a note that the numbers we give, they have to be added and subtracted and give meaningful results. So for instance, if someone has 3 cats and someone else has 5 cats, that's 2 more cats. That difference is meaningful. But let's talk about phone numbers. Phone numbers are a number. It's a quantity. But can we add and subtract phone numbers? No. So a phone number, even though it's a number, because we can't add and subtract it, it's actually a qualitative variable. Other things that would belong up here would be like license plates, social security numbers, driver's license, student IDs, because it is a number, but it can't be added or subtracted. Okay, so 2 subcategories of quantitative variables are discrete and continuous. Discrete has a finite number of possible values. So we are able to count things. So for instance, number of cats. We can count the number of cats. Versus continuous, where there's an infinite number of possibilities. And a way to think of that, remember that, continuous is a measure. So for instance, when we're talking about weight, weight is a measurement. Weight is some kind of measurement. We can say something's 5 pounds, but that could be an infinite number of possibilities. For instance, we could say something's 5 pounds when it's really 5.001 pounds. Or we would say 5 pounds if it's really 5.009 pounds. Or we'd say 5 pounds if it's really 4.9999 pounds. There's infinite number of possibilities when we just say 5 pounds. But the degree of accuracy we're looking at is the nearest pound. So continuous is a measure. Discrete, we're going to think count, because we can count the number of cats. All right, so let's look at our little breakdown of our variables. Here's a nice little chart. Our data, remember, is called a variable. We have our qualitative with words, quantitative numbers. Discrete, we can count the values. Continuous is some sort of measure. So let's flip this over and let's practice qualitative and quantitative, and then further discrete or continuous. So we're going to be doing these 2 examples, and again, I invite you to pause it and then come back and see if your answers are correct. Okay, nationality, that's our variable. How would we answer? What would the values of that variable be? Would they be numbered or words? And they would be words. So we're going to write qualitative. Next, let's think number of children. That's right. We're going to answer with a number, quantitative, that we can add or subtract. Household income in the previous year. Again, we would answer with some sort of number. So that's going to be quantitative. Level of education. All right, think post-secondary. So when we're talking about level of education, it's, you know, high school diploma, associate, bachelor's, master's, PhD, et cetera, et cetera. All of those are words. So this is qualitative. And then finally, daily intake of whole grains. Again, that's a number. So that's your quantitative. All right, so let's take it to the next level. Let's say discrete or continuous. So we're going to take our 3 quantitative variables, and we're going to take it a step further. Is it discrete or continuous? Number of children. We can count. 1, 2, 3. Household income in the previous year. Well, income, it's normally to the nearest dollar. But we also know that it can go to the nearest cent as well. Even that, we even know it could even go to 3 decimals or 4 decimals or 5 decimals, right? Especially if we have percent increases in a raise. So while our income might be to the nearest dollar or to the nearest penny, it's really rounded. So this is continuous. It's rounded to a desired level of accuracy, see the previous definition, and it's also a measurement of wealth. All right, and then finally a daily intake of whole grains measured in grams per day. Well, right there it's a measurement, so we know it's continuous. Also, you know, when we say something like 6 grams, 6 grams is rounded. It could be anything from 5.5 grams to 6.4 grams. And there's infinitely many values in between that interval. All right, so our final way to classify variables is something called level of measurement. So not only can a variable be classified as qualitative or quantitative, we also assign a level of measurement. And the levels of measurement get more and more strict. So for instance, the last level of measurement right here, it has all the same qualities as before. All right, so it just gets stronger as we go down the list. Before we look at them, only qualitative variables have the first 2 level of measurements. So I'm going to write qualitative. And only quantitative variables have the last 2 level of measurements. Quantitative. Okay, so the first one is a nominal level of measurement. That means that all we can do is name the variable. It does not allow for the values of the variable to be arranged in a ranked or specific order. All right, so nominal, we're going to think name to help us remember that. So what are some examples of a nominal level of measurement? Well, we can talk about eye color. We'll bring that one back. Because when we talk about eye color, there's no natural rank to eye color. All right, we could even do maybe the brand of car one has. All right, Toyota, Honda, Kia, Ford. There's no natural order to that brand of car or type of car. All right, the next one is ordinal level of measurement. And then the key word there, we're going to think order. It has the properties of nominal, and the naming scheme allows for the values of the variable to be arranged in a rank or specific order. So, for instance, we can do high school. When you go to high school, there's freshman, sophomore, junior, senior. Another example could be military rank. That's a qualitative variable with a natural rank or specific order. All right, so moving on to the quantitative variables. Again, it has the property of the ordinal level of measurement. And this time, an interval, think of how you calculate intervals. You look at the difference. All right, so the differences in the values have meaning. That's a little obscure. So this is what I like to focus on. A value of 0 in the interval level of measurement does not mean the absence of quantity. All right, so we can add and subtract, because that's the difference. And 0 does not mean absence of quality. So some examples of this would be like temperature, because 0 degrees doesn't mean an absence of degrees, an absence of weather. It's just, it means it's really cold out. Some other examples are clothing size, or not shoe size, but clothing size. There's size 0. It doesn't mean there's no clothing. It just means it's very tiny. And we can even look at military time. At midnight, it's like 0 o'clock. That doesn't mean absence of time, right? And even you can think of the year. Right now, you know, or at some point it could be like 20 or 2003. And if you go all the way back, you know, to like 100, year 100, year 5, year 2, year 1, year 0, it doesn't mean absence of a year. It just means it's where we started counting our years from. So that 0 doesn't mean absence of quantity. Finally, we have a ratio level of measurement. It has all the properties of the interval level measurements, and the ratios have meaning. So that means multiplication and division can be performed. In this case, this is how I like to remember it, a value of 0 means the absence of quantity. So for instance, number of children, 0 means no kids. If you had income, 0 means you don't have money. There is an absence of money. All right, so let's look at our examples. Again, I invite you to pause it, and then let's come back and check your solutions. All right, number 1, number of snack and soft drink vending machines in the school. So it's definitely a quantitative variable, so it has to be interval or ratio. 0 means there's no vending machines. There'd be an absence of vending machines. So we're going to go with ratio. Whether or not the school has a closed campus policy during lunch, it would either be closed or not closed. We can't do much with that. It's definitely qualitative, so it's either nominal or nominal or ordinal. And we can't put it in any specific order, so we're going to say nominal. Number 3, class rank. Freshman, sophomore, junior, senior, that's qualitative, and there's a natural order, so we're going to say ordinal. Number of days per week a student eats lunch, we would say a number to answer that, or values of that variable. So 0 means no days that they eat lunch. So that means an absence of days, so that's ratio. And then finally, temperature, we know 0 degrees does not mean an absence of temperature. It just means it's very cold. So we would call that an interval level of measurement.